Greetings and welcome to a new video. In this video we will discuss a very important amplifier configuration, which is the differential amplifier. We will look at the BJT differential amplifier in this video, and we will look at the fundamentals like the voltage gains, the input-output impedances, and also the conditions where we go out of our linear region into the nonlinear region. So we will see how that works in this video in clearly and detailed steps. So let's look at our outline. In this video we will look at the following topics. First we will give an introduction, so how this differential amplifier is working and what the circuit configuration is. Then we will look at the basic operation, and then we will look at two specific operations, the common mode and the differential mode operations. And we will look at the large signal analysis from there. This is the DC analysis also called. We also have the small signal analysis after that, which is also called the AC analysis. And from there, we will use the common mode rejection ratio, short for CMRR. And finally, we will also look at the input and the output impedances for the differential mode and common mode operation. So there will be a detailed video where you see a lot of aspects of this differential amplifier. So first, the introduction. Let's bring up first the circuit of a basic BJT differential amplifier. You see here two power supplies, VCC and VE, and also two inputs, VI1 and VI2. You also see two transistors, Q1 and Q2. You also see that we measure here at the collector node of the Q1, we also measure the collector node of Q2, but we also measure in between. This is the floating voltage. We also have here the RC, which is exact same at the right side for our differential amplifier. So this circuit is actually a symmetric circuit. In order to bias the circuit for the currents, we also have here a tail current, which is the IQ. Now let's go one by one and discuss this circuit in more detail. Mostly we would like to have a matched circuit. That means the Q1 and Q2 needs to be identical in order to suppress the signals we don't want. And for that we also connect the emitter nodes together here, as you can see, and then we will apply here a current, or we generate actually here a current with a realistic circuit. Now the circuit is biased using a constant current source, as you can see here, IQ, but that needs to be of course a practical circuit that can be done, usually a transistor circuit. That can be done, for example, using a current mirrors, simple current mirrors. Can be done maybe more advanced like a cascade current source, so actually two current mirrors on top of each other. We can also go for a Wilson current source, a little bit more advanced. And this is all done to create here a specific constant current source. Now the load configuration here, where we see an RC, it doesn't have to be a pure resistor. So this is not crucial for the operation of our differential amplifier. So for some applications, the collector nodes are actually connected to an active device, which is also called the active load. So it can be also connected to a transistor configuration, can be BJT, can be any other active load configuration. So in this case, we have an RC, so that means a passive load, but you can also have an active load. And that active load is now here shown, so you see an example of it. Again, the VI1 and VI2 here, and also our tail current IQ. And now the collector nodes of the Q1 and Q2 are not connected to a resistors RC, but they are actually here connected to PMP BJTs. So you see actually no resistor at all, and it is now in this case also the form we mostly encounter in chip design. And this is also called an active load because these are active devices, the transistors. Now what you also say is that the collector circuit, so the collector circuit here, is actually designed such that the Q1 and the Q2 remains always in the active region of operation. Because that is mandatory in order to also stay in the linear amplification region. So the Q1 and Q2 are not allowed to enter the saturation or the cutoff. So that means our active load or passive load needs to be designed such that the Q1 and Q2 are always in the active region of operation. That is the mandatory part. Okay, let's now go to the second part, which is the basic operation. Now we have two operations, which is the common mode operation, and we also have the pure differential mode operation. Now this is the common mode operation, so again you have the circuit here back. This is now the Q1 and Q2. Now the two inputs, which were VI1 and VI2, are now connected together to the same voltage, which is now here called VIC. The rest of the circuit configuration exact same as before. And here we see here the tail current, which will now split in two because you get exact same voltage here and also voltage there. So at the base node of Q1 and also at the base node of Q2, you get the same voltage. That means the voltage here and here, they're exact same. That means the current we have here, IQ, will also split equally for the two emitters of the Q1 and the Q2. Now that will result here in a collector current, which is then alpha times this value, because this is the emitter current, which is not exactly as the collector current, because there is a small base current here. That means we have a parameter alpha, which is then a little bit smaller than the 1. That means 0.99, for example, and that is the current which we have here in the collector. It's also for the right side, so we have alpha times, again, IQ over 2. Now, this node voltage is, we can use then the Kirchhoff's voltage law. We can say this voltage here is the voltage here at that VCC minus the voltage drop across the RC. That's actually shown here. So that is also called the VO1. Now similarly for the right side, VO2, we can express the voltage VO2 like the VCC minus the voltage across this resistor. You see actually the same expression for the VO1 and the VO2. So we can see later what it means. Now let's go first also to the differential mode operation. There you see again the same circuit. Again the tail current, again our VE and the VCC, our resistors are there. But now the input voltage for the Q1 and the input voltage for the Q2 are out of phase and they have the same value. So VID over 2. This one is actually minus VID over 2. So they are 180 degrees out of phase. Now in this case, there will be some difference here in the current. So you will get again IQ over 2. That's always the case. But a small delta I because of this small difference. And the same happens here, but since this is a negative, so that current will go down actually. Again, this delta I is a very small value compared to this IQ over 2. Now what happens here now for the collector currents on the left and the right hand side? Now similarly as we have done it for the common mode operation, we will have here alpha times the exact same value, and also here alpha times the exact same value. Now what about the voltage VO1 and VO2? Well, that is again a similar analysis. So VO1 will be then VCC minus the voltage drop across this resistor, which is then RC times the current, which is just Ohm's law, and that is shown here. Similarly for the VO2, we get this expression again using the Kirchhoff's current law, voltage law, and we apply here Ohm's law to determine the voltage. Well, how about now the differential mode output voltage? Well, the differential mode output voltage is the voltage between the two collector nodes. So in this case, it is the VOD, that's the VO1 minus VO2. Now that is from left to right, for example. Conveniently, we always choose from left to right, but it's not mandatory. Then you have here VOD, which in this case 0 for the common mode operation. Why? Because the VO1 is exactly equal to VO2. So they will cancel each other out. So for a pure common mode operation, you will not have any voltage between these two nodes. Now for the situation for the differential mode operation, you see here the VO1 minus the VO2, then you will have a specific voltage, which is then 2 times the alpha delta I RC. If you look at it, if you do VO1 minus VO2, the VCC will cancel. You also lose this alpha times the IQ over 2 here also, because that's the opposite sign. So since you do minus of that, the only thing you have left is actually this delta I times RC, but then 2 times, and again there's a minus sign. So you see there is some amplification only, so there's some output voltage only for the differential mode operation and not for the common mode operation. That's also the basic idea of the differential pair. So for the common mode operation, the common mode output voltage, which is also called the VOC, like the VOD, that's the average of the two outputs, VO1 and VO2, and we then divide by 2, so we will add them up and then divide it by 2. And that is, of course, very important statements for the differential mode and for the common mode operation. Okay, let's now go to specifically the common mode operation, and we will look at it in more detail. So this is again our circuit. You see again the voltage supply, the tail current, and the two input voltages. And if you now look at the situation for the common mode operation, again bringing back all the data like the currents and the voltages, we can say the following. Now the common mode input voltage VIC here, that is of course an important parameter because we might not know how much we can go up with this one. That depends on the following. The Q1 and the Q2 must stay in the active region, so they need to create a linear amplification. So how can we make sure, guarantee that this will always happen? Now that has to do with the situation for the VB1 and VB2 here in our circuit. To avoid saturation, that means to avoid that we enter the saturation, so we will leave the active region of operation, the Q1 of the Q2 for these two transistors, the collector voltages, that means the VO1 and the VO2, must be at least equal to the base voltages VB1 and VB2. So for the BJTs, the condition is the collector currents must be at least equal to the base currents. That's actually the condition we have to check, and also we have to fulfill. So we can say VO1 is at least so larger or equal to VB1. We can also say that the VO1 is also larger or equal to VI1. That is the same condition. That means VO1 here, which must be then larger or equal to the VIC, because that is now our base current for the common mode operation. So we are actually heading towards the maximum allowed common mode input voltage for this case. So then we can write the following. Now since we have this condition, so VO1 is larger or equal to the VIC, we can say the following. Now we know what the expressions of the VO1, that is shown here. So this expression here must be larger or equal to VIC. That is actually shown here. So let's see a good example here with numbers, so we will get a better understand what's going on. So first example, we will say now the VCC here and the VEE, they are equal to 10 volts, so that means 10 volts here and a minus 10 volts there. RC happens to be 6 kilo ohms here. We have a tail current of 2 milliamps, and we have the beta for each transistor of 100. We would like to calculate the maximum allowed common mode input voltage, which is the VIC, such that the Q1 and Q2 are operating in the active region. So we do not enter the saturation region. How do we work it out? Well, we have to check first the parameters we need here in our formula, because this is the formula we need to use. Alpha is defined or calculated as beta over beta plus 1. This is the parameter we have to calculate. And now you do here 100 over 100 plus 1, so 100 over 101. That is then approximately 0.99, so it is very close to 1. Now, then we can say VIC is then equal to that one. Now, we know VCC, which is 10, minus the 0.99 for the alpha, times the 2 milliamps, which is our IQ, and over 2, and times the 6,000, which is our 6 kilo ohms. Now, if you now do the calculation, you get here 4.06 volts. That means VIC is not allowed to go above this value, because if you enter the 4 point, for example, 1 or 2, you will get a non-linear action, and that means you will also enter the saturation region of operation. So this is the maximum allowed VIC for this situation, for this circuit. Okay, let's also look at another example where we look at another situation, because we would like to now calculate what our load resistance must be in order to stay in the active region. So the same question, but then for specifically the value of the RC. So we know what the VCC and the VE is, again 10 and a minus 10 volts. The 2 milliamps for our tail current IQ, the beta is still 100, but we have now set our VIC exactly 4 volts. So this is now a situation where this is fixed. Now the RC has to be calculated in order to get it again in the active region of operation. So what do? Well, we actually use again this formula. That is actually the important formula for this check. So we say here, well, alpha is again here 0.99 using the beta. And we can now rewrite this in order to get the required RC. So what you do is you take this part, the second part here on the left side to the right side. You place the VIC to the left side, and then you multiply by 2. And then you divide by alpha and IQ. That's actually the 3 or 4 steps all together, and actually what you see here. Now we know ECC, we know VIC, we know the alpha, and we know the IQ. So if you now substitute that here in this expression, so you get here the value we can have maximum for this RC. So if the RC is 6.06, let's say kilo ohms, and less than that, then this will do the job, and we will stay in the linear region or the active region of operation. So we have seen now 2 different examples, which will then determine if you're on the active region or not, and depending on the parameter, we can calculate what our components must be. Now let's now look at the differential mode operation in more detail. Again, our circuit here. Now we will look at the differential mode. This was a differential mode operation where you see the details for the currents and the voltages. And this was the differential mode output voltage, in this case only reacting on the changes, which is the delta I, and not on the changes of the IQ over 2. So the differential mode input voltage VID here is shown here. The first one, VI1, here this one, VI1, is VID over 2, so that's the half of the differential mode voltage. And this one, VI2, is the minus of that one, so they are 180 degrees out of phase. So VI1 is equal to minus VI2. So VID is VI1 minus VI2. That's the difference between these 2 nodes. Now taking these together here, and now we can look at the large signal analysis. So we assume that the BJTs here operating actually in the active region. And for now we will neglect the early effect to ease in, also focus on the general operation of the circuit. So the collector currents then are given by the following expression. We know this also from the diode operation. We see here the IC1, which is this current, the collector current, is equal to the saturation current value times e to the power of the base emitter voltage divided by the thermal voltage VT. Now similarly, we can do that for the IC2, which is the collector current of Q2. In a similar way, again, a VBE2. Now this is equation number 1, and we call also this equation number 2. Now for identical BJTs, so assuming both BJTs are identical, we know then that the IS1 and IS2 are identical because they are dependent on the parameters of our BJTs, of our transistors. So we can assume that, and we can also call that as IS, so no 1 or 2 anymore needed. And that is then what we have here, and we can then find the ratio of the IC1 and IC2, so the 2 collector currents as shown here. That means we have this, and we can now see that the IS will cancel here, and you get here the expression, and we can also use the identity of the exponents, and you get here the VBE1 minus VBE2 over the thermal voltage and the exponent for our value here for the e to the power. Now this we call this equation number 3. Now if we now apply the Kirchhoff's voltage law at the input loop, that means actually from here all the way here, we will result in the following. So we can say VI1 minus the VI2 is actually VBE1 minus the VBE2. You can also say the following. You can say VI1 is equal to the VBE1 minus the VBE2 plus the VI2. That's actually the exact same here, just rewritten. But what I want to say with this expression is the following, because what you see here, VBE1 minus VBE2 is VI1 minus VI2. That's also what you see here. And we know this was also, the VI1 minus VI2 was also the differential mode input voltage VID. So we can say, let's now rewrite this and call this equation number 4 first, but rewrite this ratio of the collector currents as shown here, so it's more compact. So we can say IC1 over IC2 is equal to e to the power VID over VT, which is again our thermal voltage. And that thermal voltage is approximately 26 millivolts at room temperature, approximately 300 Kelvin. We call that equation number 5. Now the Kirchhoff's current law at the emitter junction, at that node here, Q, is IE1 plus IE2, because these two come together and create IQ. That is the Kirchhoff's current law at this node. Now we know that the collector current in general is alpha times the emitter current. So we can also use here that identity. We can say the collector currents divided by the alpha will then create the emitter current. So we can say IC1 over alpha plus IC2 over alpha is equal to IQ. Now the left side and the right hand side we can multiply by alpha, and then we have this expression. Let's call this equation number 7. And then we can also rewrite this, so we have an IC1 is equal to alpha times IQ minus IC2. Or we can say IC2 is equal to alpha times IQ minus IC1. So we have here two different versions of the IC1 and IC2 using the alpha times the IQ. So let's call this equation number 8 and 9. Now we will use this expression 8, or the formula for the IC1, and we will substitute that in the formula here in equation number 5. So that's actually done here. You see here the IC1 is replaced by this alpha times IQ minus IC2, because I want to go to an expression where I see only IC2. And now you see here IC2 over IC2, that's the collector of the Q2, is equal to the e to the power VID over VT. Now we can rewrite this, so we can say this one is equal to IC2 times the e to the power is VID over T. And then you have also here, so we can replace this minus IC2 to the right side and then collect the terms in the parentheses, and you have this expression. Now we're almost done. Now we can express the IC2 in the other parameters by doing alpha times IQ divided by this term here in front of the IC2. And that's actually shown here. And this is now a very important expression for the collector current for Q2. And let's call this equation number 10. And similarly, we can say let's pick this number 9, equation number 9, and substitute that also in the equation number 5. What do we have? Well, similarly, IC1 here will stay, but IC2 will be replaced by an expression where you see also IC1. So I actually do the exact same. Similarly, I want to only have IC1 in my expression and then isolate that at the end and then get an expression like so here. So we can go again, similarly, and then do alpha times IQ minus IC1 is equal to IC1 over this e to the power VID over VT. Now if you divide that by this term, you get a minus in the exponent. That's actually shown here. Collecting again this IC1 here, so replace that to the right side and get it in the parentheses, and then express now the IC1, so isolate IC1 and express it in the other parameters as we have done it for the IC2. You get this expression. Now what do you see? We'll see actually exact same format. The only change is here the minus sign, and this is now plus. So we have here equation number 11. So this is actually a very important result, because the equation number 10 and equation number 11, so the collector currents, the formulas for the collector currents actually determine the fundamental operation of the BJT amplifier. So they are really important as our first step. Okay. Let's bring them here and then continue with our large signal analysis. We also look at the transfer characteristics of the BJT amplifier. Now this is actually shown here. You see here the red curve, which is for our IC1, and this dashed green curve is for IC2. What we see is the following. We change here the VID, so which is our differential mode input voltage. And you see here the value of each collector currents. So the maximum value what you can have for each collector current is actually the alpha times IQ, because in order to get that, this part must be then 0. That can happen, for example, for IC1, you see that here for the red one. That can happen if you make VID very large, for example, 0.1 volts already here. Then you approach almost that value, because e to the power minus that value. Now, since you have a negative in the exponent, this part will be almost 0, so you get here almost alpha IQ. Similarly for IC2, that happens when the VID is then negative. That's actually the other part. And then in the mid, you see here the alpha IQ over 2. That's the half of it, where you reach that when we have a VID of 0. Again, because e to the power 0 will be 1, so you get here 1 plus 1. You divide them by 2. That's also the same for IC2. So they will have an intersection for VID is equal to 0. What is important about this is that this is a nonlinear curve, so nonlinear relationship with the VID, which makes then the collector currents here. So we have to see where we have a part which we can use as our linear amplifier. Now if I zoom in here, we can say, well, this part looks like as a linear region. So if I zoom in here in this part, this is what I can use as our linear region. Of course, if you have a more specific specification, you only tolerate a specific error, this might be, for example, maybe a wider or maybe a narrower region for our linear region. In this case, I just have chosen this. That means our linear region for this case, as an example, is roughly between 0.02, so minus 20 millivolts, up to plus 20 millivolts. It's actually not that much, so you cannot say let's apply 1 volt, for example, here at the input, because then you go right away in the nonlinear region. What you also see is, that's the note here, the differential voltage actually of, in this case, just as 0.1 volts, so just 100 millivolts, which is actually 4 times the thermal voltage, which is then here in this case 26 millivolts, using this formula, where you see the K, which is the Boltzmann constant, the T is our temperature in kelvins, and the Q is the charge of 1 electron. You get this value of 26 millivolts approximately. So this 100 millivolts, that's actually not that much, but if you apply that difference, so VID of 100 millivolts, the most of the current will then pass through one of the branches. That will of course determine if this is a negative or positive VID. So if it is a positive VID, the IC1 will be then actually almost the tail current. And if it is a negative VID, then you get the current almost at the right side, which is at the collector Q2 for the Q2 transistor. So you can actually steer the current from one side or to the other side, depending on the value of VID. Well, it means actually the following. So for example, if I make now 4 times VT, that is now actually shown here. That means this ratio will be then just 4, so you get here e to the power minus 4. Now, if you type in e to the power minus 4, which is actually a very small value, and if you do that also here, e to the power 4, which is actually a very large value compared to 1. So that means if you now calculate that, this will be then IC1 is approximately 0.98 times the alpha IQ. Now this alpha is approximately 1. So you can say it is 98% of the tail current is now flowing here in this branch, which is IC1. If I now calculate it for the IC2, that is actually in this case, yeah, approximately 2% of the tail current. So you see, most of the tail current will be then flowing in the left branch, and just 2% of the tail current will be then in the right branch if you have here a VID which is positive. Of course, the opposite will be the case if you have a VID which is negative. We also see, we recognize the following. Since a small voltage here, differential voltage, will create a huge change in the currents from the left to the right leg of our differential pair, we can say now such a small signal can switch then the current from one side of the BJT pair to the other. That means this is actually a very fast current switch. So it's actually very useful if you want to have a fast switching in the current applications. Okay, let's now continue and look at this in more detail. Now we are also interested in the output voltage, and specifically the balanced differential mode output voltage, which is the VOD. And that will be determined by our collector currents IC1 and IC2. So we can use this expression to get also an expression for the VOD. How about VOD? Well, VOD is, as we said before, is the VO1, that voltage, minus the VO2. That's shown here. And VO1 and VO2 in the AC domain, which will be then determined as the minus RC IC1. And the VO2 is also minus RC, but then for the IC2. Now, since we subtract it from each other, we can also put it in this format. So we have now the two collector currents in the parentheses IC1 minus IC2 together, and then minus RC out of it. Now we can now substitute here the formulas for the IC1 and IC2 here. That is actually shown here. And now we have a relationship already for the VOD in terms of the differential mode input. So the differential mode output voltage is now a function of the differential mode input voltage, and of course also the collector resistance and other parameters. Now let's go here and then rewrite this further, so we can bring this alpha times IQ out of it, because they have the same here, and we can now have here 1 and 1 because we already have divided out. The next step is we will now also get rid of this minus in this exponent, so we can multiply here and here by e to the power plus VID over VT. That's shown here. Now we keep this term here as it is, and now we will recognize that the denominator here and denominator there, they're exact same. So we can here do e to the power VID over VT minus 1 over this term. So that is the next step. Now why is this now handy? Now we have an expression where we can relate the VOD over to the VID, and we can now find in the, for example, the expressions for the conditions for the hyperbolic tangent, and we recognize the tangent hyperbolic function for x over 2 is equal to e to the power x minus 1 over e to the power x plus 1. So if I now look at that and compare to this expression, forget about for a moment this, I see here that the x is equal to VID over VT. That is actually, if you compare it to the location of it, that is the VID over VT. That should be then divided by 2 in order to put it in the tangent hyperbolic function. And then we will do that. So we will actually have the following. So this, by setting x equal to that, we can now say that this is our expression for the VOD, which is minus alpha IQRC. That's what we already have outside the parentheses, times the tangent hyperbolic. And then in the argument, VID over 2 VT because of this x over 2. Now this expression is definitely nonlinear. You can see that from this expression. And now we have our compact expression which relates the VID to the VOD. Okay, let's now look at this also in great detail, because we have now our input-output voltage transfer characteristics of this BJT amplifier. So we have to look at that in more detail. So we have here now our plot. So if you have the VID here, and this is now the VOD, we can see that the curve we have found, actually the formula, is like so. So we see here a maximum value for a very negative value for VID, and it will then drop, come to a 0 value for VOD for also VID. So if VID is 0, VOD is 0. And then if you increase that, so make it more positive, then it will also drop and then becomes actually again the maximum value what can be, which is then minus alpha IQRC. So we have two extremes. The one is the alpha IQRC for negative IDs, VIDs, and for the very positive VID values, you get actually the minus alpha IQRC. In between there is again this part which we call the linear region. That's also an important part which needs to be considered. So let's again here define the linear region for this nonlinear curve. So we have here now two vertical lines. If you now zoom in here in this part, you can say, well, this part is looking quite linear. By changing the VID, I have actually a linear change in my VOD, only in this small part actually. And if you look at that, that is the linear region. And again, using the thermal voltage of 26 millivolts, because this is now for the steps in thermal voltages, you get here again this minus 0.02 and the plus 0.02. So 20 millivolts and the minus 20 millivolts. That is our linear region here in this case, of course, by estimating the values here. But you can see here in the change of the VT value, so 2 times 26 millivolts here, 3 times 26 millivolts already, actually at 4 times the 26 millivolts, I'm actually reaching already my full saturation level. So again, our linear region for this case estimated is then the minus 20 millivolts up to the plus 20 millivolts. The important part where we also discuss is the effect of the emitter resistance, because we have seen that the linear region of operation of our BJT amplifiers so far is really limited, because this minus 20 millivolts up to the plus 20 millivolts is not that much. So we would like to extend that. Now one option is to include two equal resistances RE in series with the emitters. That's shown here, so you can see here the RE and the RE, so they are now here included in our original circuit. That will allow us to extend this linear region. Of course, by including these resistances, we will reduce our voltage gain. That's the price we pay, but we will see how much that price is. Maybe that is a good trade-off to get the linear region extending to a value we want, and then we can accept that as reduction of the gain. So our input-output transfer for this differential amplifier with the emitter resistance, we will look at it now. Now for a specific case, we have a plot here, again our VID and VOD here, And now in this case, we have chosen our resistance here as 40 times the VT over IQ. So we can calculate that by having a tail current value. So we can say 40 times this 26 millivolts again, our thermal voltage, and divided by our tail current, we have a value which is an RE. The larger this value is, the larger this linear region, but also the smaller our voltage gain. Now in this case, you can see the voltage is, or the transfer is quite linear for very large regions. So the two vertical lines are actually extending between a minus 20 VT up to plus 20 VT. You can see again they are crossing here at the origin 0.0, so VID can be actually made pretty large here in the extent. So you can see that this linear region, if I now calculate that clearly again using the thermal voltage of 26 millivolts, so minus 20 VT up to plus 20 VT, which is, if you do that, it's approximately a half a volt. So minus a half, so minus 0.5 volts up to the plus 0.5 volts, which is a tremendous increase in the linear region compared to the first case. With this 0, it was just 0.02, so 20 millivolts up to the plus 20 millivolts. So this is now a huge improvement. Of course, this is a choice. This is just an example. If you do this, for example, 20 times or maybe 10 times, this linear region will go down, but your gain will go up. So this is, of course, a trade-off. But this is just to illustrate what will happen if you include that resistance here. Okay, let's continue with our analysis. First, we will look at the results for different emitter resistances, because we have looked now at one condition. Let's see also that's for several different values of the emitter resistance. So this is now our VID and VOD. You see again the plot for different values. So 2 times the VT, 4 times VT, etc. 6 times, again also in the negative side. And we can look at here different plots. So you see here now the red curve, the blue one, the green one, and the orange one. What do we see? Well, we can again see the maximum values. They reach the maximum and the minimum values, exact same values, but they have a different slope for different values of our resistor RE. That is now defined in this case. So first one is the IQ times RE, which is 0. That means actually the RE is 0. Now if you increase that, that means if I now make this product 2 times VT, then you get this blue curve, which will make this linear region a little bit larger. And if I now continue and make it 5 times VT, now again you get this green curve. And if you make it, for example, 10 times the VT, so then you get this linear region much wider. So if you increase to 20 VT or maybe 60 VT, then you get it wider and wider and wider. Well, then you also have a larger value for your RE, and that will definitely reduce your gain. But this is to illustrate again what happens if you increase your RE value, you will increase your linear region. So if you zoom in this part, you will see that the linear region will be extending by increasing the value of the emitter resistor RE. So we can also look at it in this general format or general formula. RE will be then X times the VT over IQ, where we have the X to be the multiplier for the thermal voltage, so then you can have a formula that can be used as our design parameter. Okay, let's continue in this large signal analysis. We will look now at the specific situation for just the currents IC1 and IC2. Here we see the IC1, this curve here, will go down like that. That's for this case where you have no RE. So the RE will be 0 because again, RE times IQ will be 0. If you make it RE times IQ 10 times VT, so we will look at again a different plot, which is then this one. So you see the linear region is indeed extending. The similarly is for the IC1 because that is the opposite side. And if you make it even larger, so RE times IQ is 20 times VT, then your linear region will be even larger. And it's also the same for the IC1. And they have also again the maximum values and the minimum values of alpha IQ and the minus alpha IQ. This is actually a similar plot as for the VOD and the VID plot, now just for the currents, because the only change between this plot and the previous plot is just that we had here an RC. And now we have here also the VID over the VT, which is the ratio of the thermal voltage. That's why you see here the numbers and not anymore 4 times VT or 8 times VT. Okay, so again, the results for different emitter resistance values will create a different linear region. Okay, let's continue and look at the situation for, again, adding this RE in more detail. Let's say that we have a tail current of 2 milliamps. Let's say this is our tail current source. We have selected. And we can look now at our differential mode gain if we have a different value for our RE. Now, if the RE is 0, so there is no resistor here, so this is actually our initial circuit, how much is our differential mode gain? Now, I call this A sub D, and VOD over VID is our differential mode gain. For the first cases, then the RE is 0. Well, that needs to be calculated by knowing the beta. Now we know the beta for this transistor is here 100. And we also take the RC here as 1 kilo ohm. Just an example, of course. And we have an alpha, because of this beta over beta plus 1 of 0.99 again. Now, we will look at now the differential mode gain. Now the AD will be then this one, which is then the expression we also know, which is the minus GMRC over 1 plus the GMRE. So we have to know the GM, and we also can use here the RE and RC from this example. How about GM? Well, GM is the DC collector current divided by the thermal voltage. Do we know the DC collector current? Well, we know that because this is the emitter current, and it will reflect to the collector current by this alpha. So we can calculate that. So we can say it is also alpha times the IQ over 2, because it will be here IQ over 2, and then again times alpha will be then reflected to the collector. That's shown here, and divided by the VT, and we can calculate that using this, and we know the thermal voltage is 26 millivolts. So we can know that because the tail current is known, so we can now calculate 0.99 for alpha, 2 milliamps for the IQ, and we have here 2 times the 0.026, and that will result in 38.26 millisiemens. So we have now everything for this example, and we can now calculate our AD for different configurations. Now look at that. Now first one, RE is 0, our gain is almost 36.26. If I increase it just by 20 ohms, not that much, I get here a gain which is dropping to minus 21.68. So you might now extend your linear region, but you will lose here gain, and this is a huge reduction actually. And if you go to 50 ohms, then I go to minus 13.13. And if I go to, for example, to 500, I'm almost minus 1.9. So you see the huge decrease in the differential mode gain if you increase your emitter resistance. So for the extreme case, for example, very extreme value 1 kilo ohm, you will have actually an attenuation and not a gain anymore, which is actually here minus 0.97 approximately. So it is of course important to pick your resistance here conveniently in order to also get a sufficient differential mode gain. Okay, so the larger the emitter resistance, again, the larger the input voltage range, yes, but the larger the emitter resistance will also lower your voltage gain. So that is of course again a trade-off. So there's not win-win situation. Okay, let's continue and then dive into more detail. Let's look at an objective, which is an example. So we will determine the maximum allowed differential mode input voltage for this situation. So we have here again our plot. We see here again the IC1 and IC2 as a function of the VID. So this current will change because of the change in the differential mode gain. Differential mode voltage. You see here the tangent line for this red curve. So we make a tangent line at that 0. And we try to make then this tangent line, and we try to create a linear formula. That linear formula is of course like y is equal to ax plus b. We know from linear equations. And I call this in this case IC1 lin, which is then our linear formula, which is then a times, which is our slope, times the VID plus b. So I have to know what the a is and b, then I'm done actually. Well, the a is again our slope, so we can say the partial derivative of this expression for IC towards the VID, and we will evaluate that at 0, because that's actually where I make my tangent here in this case. So let's first calculate that, and also b, we know that also that starting at, you see that alpha IQ over 2, that's actually what we can recognize already and can see from the plot. So b is known, but we have to find the a, which is the slope. So let's calculate this slope first. So we will partially differentiate this IC1 towards the VID. That's actually shown here. So we will use here the chain rule twice actually, and then you get this expression. And then you rewrite the terms, and you get also here minus and minus, so they will eat each other up, and you get this VT in the denominator, etc. Couple of steps, and then you get this one. And if I now evaluate this at VID is equal to 0, that means this is a 1. This is a 1, so you get actually 1 plus 1 squared. This is IQ times alpha, and you get here now IQ over 4 times the VT. That's the result for the slope. So I have a slope, which is A, is equal to alpha IQ over 4 times the thermal voltage. And then we have this formula, which is the linear approximate formula for this case for the IC1. So we can calculate now the maximum allowed differential mode input voltage such that the difference between the linear approximation and the actual curve, which is this part, is for example just 1%. This is an example. We can also go for 2% or maybe 0.5%. But let's see how much this differential mode input voltage can be. So that what the maximum value is in order to create just a 1% error. So let's see that in more detail. So our tangent line we already have determined. This is now our tangent formula. This is the actual formula. So we will see how that difference is such that this is just only 1%. Now we can also write this like so. We can take out this alpha IQ out of it, because then we have this format. This is the exact same as before. And now we can say, well, I need my linear formula minus the actual formula divided by the actual should be just 0.01. So I have to solve this equation. So let's substitute here the formula we have found, and also the formula for the IC1, which is the original formula, and then solve it. So we have here the formula. You see it is now, of course, a big formula. So it is, you cannot solve it by hand maybe, but you can always use a calculator. We can also massage it a bit, because we see here alpha IQ and alpha IQ here, alpha IQ, so we can all divide it out. And that's also gone. Of course, we can continue and further simplify it, but you can also say just solve it, put it in the solving solver, and then you get here a value for VID, which is here in this case 0.018, actually 18.09 millivolts. So my estimation was first, this graph was just 0.02, so 20 millivolts. In this case, I get only 18 millivolts. This is actually if you accept 1% error. If you, for example, accept 1.5% error, you might, of course, increase this. So that depends on how much error you're allowing. So if you tolerate or allow for more error, you get also here a larger VID. In this case, just 18 millivolts up and 18 millivolts down. Okay, this is actually not even one VT, which is in this case 26 millivolts. So this is not a result. So VID just only 18 millivolts. Okay, now we will look at the small signal analysis, and we will discuss first the differential mode operation. Now for that we will really need to look at the small signal circuit. So we will go from the actual circuit to the small signal. There we will disable the DC source, so there will be a short. And this IQ here will be then replaced by its output impedance. I call this in this case RQ. So that has some output impedance. So the actual current source will of course have an output impedance. In this case we will model that by RQ. We'll also model each BJT by an RPi and a controlled source, which is the beta times IB, which is this base current. Similarly for the Q2. We also have the VID over 2, and also here the VID over 2 of course flips, so we get here minus VID over 2. So we will now analyze here and try to get the values for the differential mode operation. Now for a pure differential mode operation, the potential at node P is at ground potential. So it is actually virtually 0 volts. But why? Why is that? So can we prove it? Of course we can prove it. Let's do that. Let's use a very simple circuit. So let's say we have here the resistor RE and RE, and there's an RQ here. So it's actually similar to this situation. And we know if this voltage goes up, we also have a voltage going up here in a positive sense. If this voltage is going down, we have also a voltage going down in this sense. So it means the voltage is going up, for example, here by 5 millivolts, then this is then going up by a specific value, volts, and this is then of course going down by the minus 5 millivolts, and then the same decrease here you have here as the same increase here. So it's actually the same level goes up here and down here. That means I can create here two sources, VA and VB, but they are opposite. So I can say this is 10 millivolts, just an example to make it convenient, and this is the minus 10 millivolts. This should be of course anti-symmetric. So VA is equal to minus VB. And then I have exact same resistance, RE and RE, and I have here some RQ. The value of RQ here is not really necessary, also not really important. So let's see what then the voltage is at node P, because I have to prove that this is indeed 0 volts. What can we do? Well, let's designate first the Q current, IQ, I1 and I2, so this is just a random choice. Then I can say, apply Kirchhoff's current law, KCL at node P. I can say, well, I1 and I2 will create IQ. That's shown here. So I can say I1 and IQ will make IQ, and I can say I1 is actually VA minus VP over RE, and this current I2 is VB minus VP over RE. That's equal to VP over the RQ, because that's the current using Ohm's law. But I see here the RE and RE here as a denominator. They have the same denominator, so I can bring this together in one equation. So I have here VA minus VP plus VB minus VP. What do you see? Well, the VP here is actually 2 times, and I see here VA and the VB. But we know VA is minus VB. That means this is also minus VA. So they will actually eat each other up. So you actually get here minus VP minus VP, which is then 2 times VP, because this VB and VA are gone. And again divided by the RE for the left side, and you have here VP over VRQ on the right side. Now if you look at this equation, what is the solution here? Of course 0. That's the only solution to make this equation valid, because you cannot say let's make it 1 or 2. The only solution here is 0. So that's also the proof that the VP is indeed 0. This is again our proof for pure differential mode operation. The point P is at ground potential. Okay. Now, it is helpful and convenient to look at the half circuit for the differential mode and also for the common mode operation later if you have a pure and symmetric circuit. Now, we have a symmetric circuit, and this node P is grounded, virtually grounded, so we can actually split the problem and divide it actually in 2. So that's actually what we call the half circuit. So we could go down and we can say, well, let's use the left side only, for example. And since P is virtually ground, so we can say this is the ground node. And then we have this circuit, and this is more convenient to work with than this complete small signal analysis and small signal circuit. So let's bring it here and make it larger, and then work on this one and then calculate the necessary parameters for our differential mode operation. We start first with a single-ended differential mode voltage gain. That is the VO1 over the input voltage differential. So that means differential mode single-ended. That is the format I am using. That's sort of the coding. That's the VO1 output voltage at the collector node divided by the differential mode input. Well, the output voltage, looking at that one, is the minus, because this I measure here from here to ground, so my current flow will be actually in this direction, but the current itself goes down, so I have a minus sign, minus the beta times IB1, because that's also flowing here, times RC, that's my voltage using Ohm's law. Well, this current here is our AC emitter current, IE1. That is also beta plus 1 times IB1, because this base current and the collector current comes together and creates this current. So you can see that this is indeed beta plus 1 times IB1. Then I can say the following. Well, this voltage VID over 2, which is our half of the differential voltage, is then the IB1 times R pi plus the voltage, which is then across the RE, which is then this current, emitter current, times the RE. Well, I use the emitter current expressed in the base current, that's actually shown here. So I can now collect now the terms together. So taking out the IB1 out of the parentheses, that's shown here, and I also multiply left and right hand side by 2. So I have now an expression for VID And also I have an expression for VO1. So let's now put it here and see what happens. So we have a minus beta times IB1RC divided by this expression. You see the IB1 can cancel, and then we have an expression for the differential mode voltage gain single-ended. And you see again this minus, so we have a sign inversion. Okay, now for the balanced differential mode voltage gain, what do? Well, you have to look at the differential VOD. That's this part or this part if you look at the small signal circuit. So let's start with that, and again using the coding, so differential mode balanced. Okay, VOD over VID, so not VO1 anymore or VO2, but just VOD. We always have VID for our input. So by symmetry we can say the output voltages are given by VO1 is equal to minus VO2. Why? Because if this is going up, this node will go by equal amount down. So that is of course the effect of pure symmetry and pure differential operation. So VO1 is minus VO2. That means for our differential mode output voltage, we can say the VOD is VO1 minus VO2. That's the difference. And since VO1 is minus VO2, that means this is also plus VO1. So that means we have here 2 times VO1 or minus 2 times VO2 because VO1 is equal to minus VO2. Now I can use now the expression for VO1 here and then double that and put it here in the numerator for our balanced differential mode gain. And I also get the expression for the VID already have. So I can now put it here. And you see now the 2's will cancel. And I have now an expression for my balanced differential mode gain, which is the minus beta RC over this. And you can now see that this, the balanced differential mode gain, is 2 times the single-ended differential mode gain. So that is the nice observation we can use later. Alright, let's now also look at the common mode operation. We start always with a small signal circuit. Now for the common mode operation we have 2 inputs at the same voltage source, which is the VIC here. So they go up and down with the same level and also in the same direction. So they have the same phase. And what we had before was this point P was connected to the output impedance of this tail current IQ. We call that RQ. And in order to make here a split, since this node P is not anymore virtual ground, we can create here cleverly 2 times RQ in parallel. So 2 times RQ and 2 times RQ in parallel, which will again create 1 RQ. That will allow us to split the circuit again, and we get here a nice symmetry. That will also allow us to say that the current flow here is 0. So we again will try to use, and that is the objective, half circuits. In order to make that, we need to split this, what we had before here, just 1 RQ into 2 RQ, 2 RQ here. So our half circuit for this common mode input will be done like so. So this is almost the same as for the differential mode condition. Now we don't have this ground here. Now we have here 2 times RQ. The rest is exact same. Okay, let's now again focus on this half circuit and then try to get the voltage gain. First we start with the single-ended common mode voltage gain. That will be then given by A, C, which is the common mode, and S for single-ended. That's the VO1 over VIC. Again, the same procedure as we have done it before, because the VO1 is the same, minus beta IB1 times RC. And how about then the other? So again, this emitter current will now flow through the resistor RE and also through the resistor 2 times RQ. And that's again the same, beta plus 1 times IB1. So VIC here is equal to IB1 times R pi plus the voltage across these 2 resistors together, which is then RE plus 2 times RQ times the current here, which is the emitter current. Now let's again take out the beta here, the IB here, which is the base current, and then you have here the expression, because we know the VO1, we also know the VIC, that's shown here. The only difference between the situation for the differential mode and this one is that we have now here this 2 times the RQ. And also we had here a 2 here in front. Again, we divide here the base currents, IB1, and then you have here the expression for the common mode single-ended voltage gain. Well, how about the balanced common mode voltage gain? Now we know the common mode voltage gain can be calculated for a single element and for the balance, and we can use the situation for the output common mode, because the output common mode voltage VOC is the average of the VO1 and the VO2. That means VO1 plus VO2 divided by 2. That means they are exactly equal to each other. So it means VO1 is equal to VO2 is equal to VOC, because we have the same input for the two base nodes for our transistors. So since both inputs are the same and also in phase, the output voltage are exactly the same. So we can say again VO1 is equal to VO2. That's also equal to the VOC, because that's the average. So we can now say VO1 is also VO2. Now from there we can say that the expression we have now is exact same as before. So the single-ended common mode voltage gain is exact same as the balanced common mode voltage gain. So we have now here the expression also given. So again, ACB is equal to ACS. Okay, let's now look at the next topic, which is our common mode rejection ratio. In this case, that is for short CMRR. And now we have here a patient line. So this is a practical situation where you have here two leads going from each arm, and that can be coupled, for example, to a source, which is here also connected to the ground. And we have now here two inputs, VI1 and VI2, as we have it in our differential amplifier. But we also have coupling, which we do not want, like this capacitive coupling from the ground, maybe some capacitive coupling from our lamp, or maybe from a power cord, anything we do not want. Those are all common mode inputs. So with real differential amplifiers respond, of course, to common mode signals and also the differential mode signals, not just for differential mode, because this is the information we would like to process, but this is the information we get, but we do not want to have it. Now the output voltage is then the summation of the differential mode gain times the differential mode voltage plus the common mode gain times the common mode voltage. And this is what we like to have much smaller, preferably 0, compared to that part in the differential mode. So we have here AD and the AC as shown here. Now for a well-designed amplifier, AD is much larger than the AC. Now the quantitative specification we would like to use, that's the objective of this section, is the common mode rejection ratio, CMRR. And that is the ratio of the differential mode gain and the common mode gain. And it's given as this ratio, just simply AD over AC. So if you make this larger, much larger, then your system is also rejecting the common mode signals much better. So this is also given in the dBs, just 20 log of that value, and this is also more convenient, which you see most often in the datasheets of the amplifiers. So example, we have a differential amplifier. Let's say it has a differential mode voltage gain of minus 1000. It happens to be also that our common mode voltage gain is minus 0.01, so 1 over 100. Each, of course, negative here. Then we like to calculate the CMRR, so the common mode rejection ratio in dBs. Now we can use this formula and then do 20 log of that, and we get our result. So here the solution, AD is minus 1000, AC is minus 10 to the power minus 2. And if you now substitute here the value, you get here this, which is then 10 to the power 5, which is then 100,000. If you convert that to dBs, you get 20 log of 10 to the power 5, which is then 100 dB. So that means the higher our CMRR, the better our amplifier is in rejecting these common mode signals and focusing only to process the information, which is our differential mode signal. So going up to another situation, so let's say we would like to have a specific CMRR. So we would like to know how much that should be. So in this case, we have an electrocardiac amplifier, ACG amplifier, and we know our differential mode gain is 500. And we also know that our differential mode input signal happens to be 4 millivolts peak, quite small. But our common mode input signal, we know from this power cord or any other part of the system, is 100 volt peak at 50 hertz, which is a sine wave, which is quite large. So now the problem comes, and we like to know the output voltage contribution from the common mode input should be no more than 1% of the output voltage caused by the differential mode input. So this is now a really strict specification. How do we solve this problem? Well, the desired output voltage is calculated from the data we have from our differential mode operation, differential mode gain and differential mode input. So we can say, well, the output voltage VOD is AD times VID, which is 500 times 0.004 is 2 volts. So we use these two data to calculate this output voltage if you only focus on the differential mode condition. But to meet the specifications, so we accept just maximum 1% error in the output, that means this value we have to have only 1% of it at the output because of the common mode operation. That means our output voltage is allowed to be 0.02, just 1% of the 2 volts. So that means our common mode gain must be then the output common mode divided by the input common mode. Now input common mode is 160 volts and output common mode is allowed to be maximum 0.02. That is then in this case 1.25 times 10 to the power minus 4 as our common mode gain. That's the gain we can have maximum. So the lower the better, of course. Now if I continue and then look at the required CMRR, that should be then using the formula we already have discussed, just a ratio. So we have here 500 over this 1.25 times 10 to the power minus 4, you get here 4 million, so 4 times 10 to the power 6. If you convert that now to dBs, you get here 132 dB. So if I have an amplifier which has only a CMRR of 120 dB, this is not sufficient. So I have at least this 132 dB. Now this is now a practical situation looking at the specification, and you have to find a good amplifier which can create this CMRR. Okay, now let's also look at the situation where we see differential mode operation, the common mode operation, and also the single-ended and the balanced CMRR. So I have now 4 parts I would like to discuss next. So for our differential mode operation, our single-ended differential mode gain was this, and for the balance it was that, and for this is now the actually sort of the summary for all the parts we have already discussed. And now we can see how we can now define our single-ended CMRR, so single-ended common mode rejection ratio. Now that is then put like so. So we have the single-ended common mode rejection ratio, which is then the differential mode single-ended. We take it actually from this expression divided by the common mode single-ended. So it is just this divided by that. So you will see minus beta RC will divide it out. And so you divide by the fraction, this will be flipped and coming actually here in the numerator, and this will be in the denominator. That's shown here. So this is the expression for the common mode rejection ratio single-ended. How about balance? Well, similarly, you get here the balance differential mode gain and the balanced common mode gain. You put it here in the expression, and you have here again this expression. You see again this is 2 times larger than the single-ended common mode rejection ratio. That's again our observation. So the balance is always 2 times better than the single-ended version. Okay, let's now also look at the differential mode input-output impedances. So this is again our circuit, BJT amplifier, and this is our small signal circuit for the differential mode operation. And how about our differential mode input impedance? Well, if I look at the input impedance of any circuit, I look actually between the 2 nodes of my input, which is then between the left P and the right B node. So the left and the right base node. So I look between them, and I know this is of course virtually ground. So I can say I see R pi, RE, RE, and R pi all in series. That means I have now here the condition, which is then defined as the impedance Z input for differential. That is the ZI of VID over IB1, which is actually this current. Now, well, that means then it is 2 times the R pi. Of course, this is then beta plus 1 times larger. And I have it actually then 2 times because I have it again here. That's the expression for the input impedance for my differential mode condition. How about then the output impedance? Well, output impedance we will look actually between these 2 nodes. We have here 2 conditions. We can have it as single-ended and balanced. Single-ended I define it as ZOD, so ZOD single-ended, so output differential single-ended, and the other one is output differential mode balance. If you look at the single-ended, that means if you look between this node and ground, that is only actually RC because you go from here to ground. If you look between these two nodes, you see actually here this RC and RC, so 2 times RC. That's for the differential mode operation for the input and output impedances. Now let's look at also the common mode circuit. Again, our small signal circuit then for the common mode operation. Let's also look at the input impedance first. How about that? Well, now we do not have anymore here a virtual ground, but we have the same voltage here and the same voltage there. That means our half circuit is actually now in parallel. And since we have the same impedance from this node to ground, we actually have then the impedance from here to ground divided by 2. That's actually what I see here. So you see here R pi plus RE in series with 2 times RQ. That's actually what we had in our half circuit, and then times, of course, beta plus 1. That's what we have seen. And we have it also on the right side. And since they are exactly equal to each other, so 2 resistors equal to each other, that's the half of the resistance for the parallel case, and that's actually what you see here. Now for the common mode output impedance, we look at the single-ended, and for the balanced, this is the exact same result. Now using, of course, also the correct indexing, which is the O output, C for common mode, and S for single-ended, O, C, and now this for B for balanced. Okay, let's now look at the summary. So we will bring now everything here together. You see here the differential mode gain, common mode gain, and the common mode rejection ratio for single-ended and the balance. You see here all the formulas we have discussed so far. Also here for the input and output impedance for the common mode and differential mode gains. So we have here now the complete picture for this BJT differential amplifier. Alright, what's our example? Considering the fundamentals of the BJT differential amplifiers, we have discussed in great detail how this circuit works and what the condition is for differential mode and the common mode gains. We have looked at the small signal model and used the half circuits to determine the parameters for this circuit. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.